Every time you see a car crash test on TV or a rendering of a new airplane wing, there's this incredible hidden process making it all possible. And today, we're going to pull back the curtain on that process. We're talking about meshing. It's one of the most critical, yet almost always invisible steps in all of modern engineering.
And look, you just can't overstate how important this is. Our source material really hits the nail on the head with this quote. All simulation accuracy, it begins with meshing. If you get the mesh wrong, your results are not just a little off, they could be dangerously misleading. But if you get it right, oh man, you can unlock some truly incredible insights into how things work in the real world.
So what exactly is meshing? Well, think of it this way. A computer can't really understand a perfectly smooth, complicated 3D model from a design file. It's just too complex. So meshing creates what we call a digital skeleton. It breaks that smooth model down into a huge number of tiny, simple pieces called elements. It's a way of translating our messy, complex reality into a language the computer can actually understand and solve. All right, so here's our game plan for this explainer. We're going to start with why we need this digital skeleton in the first place. Then we'll meet the little building blocks that make it up. After that, we'll get into the art of creating the blueprint. We'll even meet the master builders, the software that does the work. And finally, we'll talk about the big choices an engineer has to make.
Okay, first things first, the why. You see, a smooth 3D shape for a computer is basically infinitely complex. It has no simple way to calculate things like stress or heat on a continuous curve. So by creating a mesh, we're building a finite blueprint made of simple, predictable shapes. This lets the computer run its physics equations, like for stress or fluid flow, on each tiny piece, one by one. Then it just adds up all those results to give us the complete picture.
So, if the mesh is our skeleton, what are the bones made of? Let's meet the building blocks. I like to think of these as the digital Legos that an engineer gets to play with. They're the fundamental element shapes used to build up the entire mesh, and they come in a few really important varieties.
And right away, in the world of 3D meshing, you've got this classic showdown, this fundamental choice between two main characters. On one side, you have the tetrahedron, which we can call the autofiller. It's like a little pyramid, and it's amazing because you can use it to automatically fill literally any shape you throw at it. But on the other side, you've got the hexahedron, the gold standard, a perfect little brick that gives you incredible accuracy. But it's a real pain to try and fit into complex shapes.
So let's talk about the tetrahedron, or TET for short. Its superpower is automation. Seriously, it's the go-to element when you have a super complex part and you just need to get it meshed fast. But there's a downside. In its most basic form, a TET can be a little too stiff in a simulation. That means it might not deform as realistically as it should, which can, mess with your accuracy. Now, on the other hand, we have the hexahedron, or hex. And trust me, this is the gold standard for a very good reason. It gives you super accurate results, and it's computationally efficient, meaning your computer solves it faster. The problem? Well, just try filling a complex, curvy object with a bunch of perfect little bricks. It's a huge challenge, and often an engineer has to go in and build that mesh by hand, which can take hours.
Now, beyond just the shape of the Lego brick, engineers also have to choose its quality, or what we call its order. The most basic type is a linear element. It's simple. It only has connection points, or nodes, right at the corners. This makes it super fast for the computer to solve, but it's terrible with curves. Imagine trying to draw a circle using a bunch of short, straight lines. That's kind of what a linear element does.
But for better accuracy, you can upgrade to quadratic elements. The big difference here is that they have extra nodes, not just at the corners, but along the edges too. These extra points allow the edges of the element to actually bend and curve. This means they can capture the true, smooth geometry of your model way more accurately. Of course, that extra accuracy comes at a price. More nodes mean more calculations, and that means longer simulation times.
So, what do you do when you want the best of both worlds? Maybe you want those beautiful structured hex bricks in one area, but you need the easy automatic TET pyramids in another. Well, this is where the unsung heroes of meshing come in. You've got Prism and pyramid elements. They're like the perfect diplomats, the connectors that can build a seamless bridge between the two, letting you create these awesome hybrid meshing.
Okay. So we've got our building blocks.
But how do we put them all together? This takes us to the art of the blueprint. See, creating a really good mesh isn't just about clicking a button and letting the computer go wild. It's a real engineering art form that involves setting up a whole bunch of detailed rules and controls to guide the process.
Engineers use two main levels of control here. First, you have your global controls. These are the big picture rules for the whole model, like saying, okay, in general, I want my elements to be about this big. But then, for the really important areas, you use local controls. These are specific instructions for critical spots, like telling the software to make the mesh much, much finer right around a shirt corner. And these local rules always override the global ones.
A really key control is something called the growth rate. A typical number you'll see is 1.2. So what does that even mean? Well, it's a simple rule that says as the mesh grows from a fine area to a coarse area, each new layer of elements can't be more than 20% bigger than the layer before it. This little rule is crucial because it stops you from having jarring jumps in size, which can cause big errors, and it makes sure you get a nice, smooth result.
So how does an engineer actually put all this together? Well, a pretty standard workflow is to just layer these controls on top of each other. You start by setting a global size to get a baseline mesh. Then, you tell the software to add a refinement to better capture all the curves. After that, you add another refinement to handle any narrow gaps. And finally, for something specialized like fluid dynamics, you might build these thin, highly organized boundary layers right on the surfaces that matter most. Each step makes the final mesh smarter and better.
So we have our blueprint, we have our building blocks. Now we just need the master builders. And these are the software tools themselves. Each one has its own unique philosophy, its own different approach to building that perfect digital skeleton.
Let's quickly compare these builders. Think of Ansys Workbench as the user-friendly one that gives you great results without a lot of fuss. Then you have tools like Abacus and Hypermesh. They're for the precision perfectionists who need total manual control. Star CCM Plus is a total specialist, built from the ground up to create amazing meshes just for fluid dynamics. And then you have OpenFoam, the powerful, free, open-source option for the experts who want to build and control absolutely everything themselves.
And this brings us to our final stop, where everything we've talked about really comes together. Because at the end of the day, meshing isn't just some technical task you check off a list. It's a huge engineering decision that's all about balancing three competing factors. It all comes down to a series of really important trade-offs. The choice of elements, that's a balance between automation and accuracy. The choice of parameters, that's a balance between precision and speed. And the choice of software, that's a balance between it being user-friendly and having total control. And here's the key takeaway. A good mesh is rarely the most perfect mesh. It's the best possible engineering compromise between accuracy, time, and of course cost. So, this all leads to a really big question about the future. As AI gets smarter and more powerful, what happens to this art of meshing? Will artificial intelligence eventually automate all of these complex trade-offs, turning it into a pure science? Or will the intuition, the experience, the human touch of an engineer always be essential to building that perfect digital skeleton? That's something to think about. Thanks for joining this explainer.